All right, so last time, I think it was last time, we did these Hecke correspondences. So TP was a correspondence from the modular curve x0n to itself. And we only did this over the complex numbers, but the same definition works over the rational numbers. I'll review it later today. So the definition makes sense over Q. And that implies that this correspondence of the curves induces an endomorphism of the Jacobians. So you get the endomorphism of J0n over the rational numbers. And now this J0n has good reduction away from n, because the curve x0n is smooth over z join 1 over n. And so you can extend it by its Néron model, say, to z1 over n, and this TP will extend to an endomorphism over the integers. So J0n extends to an abelian scheme over z join 1 over n, and TP extends to an endomorphism over the space also. So now we can reduce mod any prime away from n. And the Eichler Shimura Theorem tells us what the reduction of TP is mod p. So precisely, it says that TP is equal to f plus v on J0n over fp, where f is Frobenius and v is the Verschuren. Okay? All right, so our first goal today is to prove this theorem. And I'm going to start with a lemma. So the way that I've defined TP kind of integrally is a little funny. I mean, we defined it over Q and then we kind of extended abstractly. We'd like to know that we can actually compute it by a correspondence over FP. And so the first thing I want to say is that sort of the obvious thing that you guessed does work. So I'm going to state this lemma kind of abstractly. So suppose that O is a complete DVR. We're going to have ZP in mind. Let K be its fraction field, and little k is the residue field. And suppose we have a smooth proper curve over O. That's going to be like x0n for us. And suppose that we have a correspondence. So f and g are two finite flat maps from some curve y to x. All right, and then I'm going to let jk be the Jacobian of x over k, and j over O is its Néron model, which is just take of x, take 0 of x. It's an abelian scheme over O extending jk. So this correspondence here, if I think of it over k, over the generic fiber, I can use that to build an endomorphism of jk. So I'm going to call that hk. So hk is the map jk to jk given by f and g. So remember that was like this pull back, push forward type thing. And h is going to be its extension to j. Okay, and now finally, suppose that we have a divisor of degree 0, d0, on the special fiber of x. So this gives us a point on the Jacobian, the special fiber of the Jacobian. I'll call that x0. And then the point is that if I apply this h to x0, so then h of x0 can be computed by doing pull back, push forward of d0. So this point on the Jacobian, I'll say, is represented by the divisor G star F upper star of D0. Okay? So here's the proof. So I'm going to lift D0 to a divisor on X. So let D, so this is going to be, I mean, we need to use some kind of relative version of divisors here. I'm not going to go into the technical details, but so this is supposed to be a divisor on X relative to O. So let D be a relative divisor on X, lifting D0. You can lift it because we're assuming X is smooth. And I'll let D prime be the push forward pullback of D. Okay, so you have to give some definitions for what this means in the relative situation, but you can do this. And this is again a relative divisor on X. I mean, it should be like flat over the base and a divisor in each fiber. Okay, so these two guys define points in the Jacobian J. So D prime define points X and Y in J. And sort of by definition, H of X, so this is again a section of J over O, and it's the unique section extending what it is in the generic fiber. And this thing, I mean, this thing was defined by the push-pull formula. So hk of xk is the point on the Jacobian. So it's represented by the divisor, G star F star of D over K. But that's clearly equal to this thing yk, just because y is defined as this. And y is an O section of J extending yk, so it must be that y is equal to h of x. And so now if I just pass to the special fiber, we get what we want. So h of x0 is what you would call y0, just the specialization of y to the special fiber, which is equal to G star F star D0. Okay? Okay, so now we're going to try to apply this. And the idea is that we want to find an integral representation for the Hecke correspondence and fit that into this lemma. So let me recall the notation that we had. So M0 n bar was the moduli stack. Of elliptic curves with gamma 0 n structure, generalized elliptic curves. And this was a proper DM stack over the integers. And then M0 n bar was the coarse space, which I'll write like this. And this M0 n bar is basically the same thing as X0 n, but I'm going to follow Mazur's notation and only use the notation X0 n when n is inverted. Well, I mean, yeah, okay. All right, so there's a map of stacks from M0NP to M0N, even with bars, which forgets the level P structure. So precisely, I mean, this takes a pair E, G to E. So here I'm thinking of E as an elliptic curve with level N structure. I'm just going to leave the level N structure implicit for a while because it's just going to go through everywhere. And so here G is the gamma P structure. This is an elliptic curve with gamma 0 N. And this is gamma 0 P. And then I'll write F for the map that this thing induces on the coarse space. So this goes from M0 NP to M0 N. And then there was a second map that you can define. I'll call that G tilde. This goes from and to the same place. And this one takes EG to E mod G. And I'll let G be the map on the coarse spaces that it induces. Okay, so we get this correspondence. Like this. And over the complex numbers, this is exactly the Hegel correspondence that we defined previously. So but this is all defined over Z now. And so, in fact, these F and G are finite flat maps. So I haven't proven that, but in that you have to analyze the space of gamma 0 P structures on an elliptic curve and show that it's relatively representable by a finite flat thing. But let's just take that for granted. And so that means that we can apply this lemma that I just proved. So by lemma, TP is computed by G lower star, F low upper star, even in characteristic P. Okay? Any questions so far? All right, so now we're going to use what we know about the structure of M0NP in characteristic P. So we did this a little before, but I'll do it again now. It's basically just two copies of M0N. All right, so you can define two maps in the opposite direction. So I'm going to call them now I and J. So first, on the stacks, I tilde goes from M0N to M0NP. And so it takes an elliptic curve, and it has to give an elliptic curve with gamma 0 P structure, and you take the kernel of Frobenius. And I is going to be the map that induces in the coarse space. And J is the other one. And it takes an elliptic curve, and it gives you the elliptic curve EP, this twist, and the kernel of the Verschuvel. And so we showed, I mean, this is easy, you just trace through the diagrams, that if you do F then I, you get Frobenius, you get the identity. If you do G and J, you get the identity. If you do Fj, you get Frobenius. And if you do Gi, you get Frobenius. Where this Frobenius is on M0n. Okay, so the fact that Fi is the identity means that I is a closed immersion. And similarly for J. So you have these two copies of M0n going into M0np. And if you remember, we looked at what the possible structures, gamma 0p structures were on ordinary curves, and there were exactly two. And one of them is being hit by I, and one of them is being hit by J. So in the ordinary locus, I and J are these closed immersions that hit every point. So it gives an isomorphism. Well, let me write it. So write M0n ord for the space where the points are ordinary elliptic curves. So this is the open subscheme of M0n bar represented by ordinary elliptic curves. And similarly for M0 and P ord. So what I was just saying is that Ij gives a map from M0n ord disjoint union itself to M0n P ord. Which we know is a closed immersion and hits all the points. So it's an isomorphism. So we're going to look at what this Hecke correspondence is on the ordinary locus using this description of the total space. So this thing here is M0np ord. And this is supposed to map down to M0n and to M0n. So, okay, so to give a map like this, I have to give a map from each component down. So let me draw the arrows like this. So this copy of M0n ord is from I, say, and this one comes from J. And this map here is supposed to be F. So when I look at what this map does to this thing, I'm really doing I and then F. And over here I'm doing J and then F. So this thing here is going to be the identity, and this one's going to be Frobenius. And similarly, the other way, it's just backwards. So this one's going to be Frobenius, and this one's the identity. So this says that this Hecke correspondence TP, well, it's really the disjoint union of two different correspondences, right? I can just think of this correspondence and that correspondence separately, and it's just kind of the union of those two. And so the first one is identity Frobenius, and the second one is Frobenius identity. And here I'm writing plus instead of disjoint union, which kind of makes sense because if you think about how this works on divisors, it does work as a plus, right? If I have a divisor here and I pull it back to here, right, it's going to be the sum of the pullback here and the pullback here, right? And so then I push forward and it's still the sum under these two different correspondences. So if D is a divisor in the ordinary locus, then Tp of D is equal to the action of this correspondence on D plus the action of the other one on D. But these are just Frobenius and Verschuebung. I mean, that's how they're defined on divisors, by these correspondences. So this shows that Tp equals F plus V. This equation holds on points in J0n, which are represented by divisors in the ordinary locus. But every divisor is represented by one in the ordinary locus. I mean, because I'm allowed to change by equivalence of divisors. And if I take a curve and take any divisor, it's linearly equivalent to one where I avoid any finite set of points. So every divisor linearly equivalent to one supported in the ordinary locus. Okay, so that proves it. Questions? Well, here I'm working with the coarse spaces. So this is just a nice open curve over FP. Any other questions? Okay. All right, so now I want to use this to say something about the Tate module of J0n. Just in characteristic P. So I'm going to let VL be the rational L-adic Tate module. So it's the Tate module of J0n just over FP with L inverted. So this is a QL vector space. And since T, the Hecke algebra, it acts on J0n by endomorphisms, so that action is going to carry through the Tate module. And so I get an action of T tensored up with QL. So this VL is a TQL module. And last time we showed that the Tate module of J0n was free of rank 2 over the Tate module. So that this is free of rank 2. Okay, so the Frobenius also acts on the Tate module, right? And it commutes with the action of T. So I can think of VL as this free module of rank 2 over this commutative ring, and I have this thing commuting with the action of the ring. So I can think of Frobenius as a 2 by 2 matrix with entries in this ring. So I can think of F as in GO2 TQL. Is there a question? Okay. And so we know from this Eichler Shimura theorem, well, I wrote it as Tp equals F plus V. I can multiply this through by F on each side. So that says that FTP is F squared plus FV, which is P. So it says that F squared minus TPF plus P is 0. So F is a 2 by 2 matrix over this ring, and here is a quadratic polynomial that it satisfies with coefficients in that ring. So you'd like to say that this is the trace and that's the determinant. But that doesn't come for free, right? I mean, even if you had a complex matrix, it wouldn't necessarily be the case, because you could have a diagonal matrix, and that would satisfy a linear polynomial, and then you could multiply it by any other linear polynomial and it would still satisfy that equation. The coefficients wouldn't give you the trace and determinant. But in this case, it does. So what I want to say is that what you'd expect to be true is true. So the trace of Frobenius on VL is TP, and the determinant is P. All right. So we have the Weil pairing on VL. So it's an alternating pairing. It takes in two guys in VL and gives you something in the Tate module of GM. That's what this one meant, the Tate module of GM. And so I'm using, all right, so the TQs, can I use Q for a prime number? I'm already using P and L. So the TQs for Q not equal to N, not dividing in, let's say, are self-adjoint with respect to this pairing. Okay, so let me explain why that's the case. So TQ is computed, I mean, so if I'm thinking of it as an endomorphism of the Jacobian or of this VL, it's computed by using the correspondence that defines it. So it's computed by, say, this FQ, GQ. So here, earlier in this lecture, I defined F and G, right? But I can do that for any prime, so FQ and GQ. And it's, I mean, just by kind of generalities, its adjoint is defined by GQ, FQ. I just flip them. That gives me the dual thing on the Jacobian. And so, I mean, if you think about what this is doing, I mean, how these are defined. So TQ here, this is like, if I want to evaluate TQF at some elliptic curve, I'm supposed to sum over all the P isogenies from the elliptic curve. So this is like summing over P isogenies out of E. And this one's going to be like summing over P isogenies into E. But those two sets are the same by the dual isogeny construction. And so you're really summing over the same set, and that's why these two things are equal. Okay, so that means that if I define phi to be the map from VL to its dual, that takes X to the linear form given by pairing against X. So this is I mean, since this form is non-degenerate, this is an isomorphism of QL vector spaces. And the fact that these T's are self-adjoint says that it's an isomorphism of T modules. And this thing also has the property that if I do phi of f of x, I get v of phi of x. So the reason for that, I mean, phi of f of x is some linear functional on VL, and it's the one that takes y to the pairing of y and fx. And then this I can write as 1 over p times fv y paired with fx. Right, fv is equal to p, so I can just stick in an fv and divide by p. And then the Weil pairing has the property that if this Galois equivariance, I can pull the Frobenius out. And the way that Frobenius acts on a system of L power roots of unity is by raising to the pth power. So the Frobenius pulls a p out. This gives me vyx. And so that's just vx on vy, which is v of x on y. So anyway, this implies that the trace of Frobenius on VL is equal to the trace of the Verschurbung on the VL dual. Because phi is intertwining these two actions. But now, so VL is a free module of rank 2. If you pick a basis for it and compute the matrix of V, and then you take the dual basis and compute the matrix of V on the dual space, you just get transposes. So the matrix for V on VL is the transpose of the matrix of V on VL dual. So in particular, their traces are the same. So that says that the trace of Frobenius on VL is equal to the trace of the Verschurbung on VL. And so now I use the Eichler Shimura relation, and I take the trace of each side as operators on VL. So here I get trace of TP, and here I get trace of F, plus the trace of V, which is 2 trace of F. And the trace of TP is what? Anybody? 2 times TP. Can someone else tell me why that's true? So if I have a commutative ring R and a free R module of rank 2, an element of R is going to act on that by scaling. Right? And so it's the diagonal matrix. So TP, normally you think of it as some complicated operator, but here it's in kind of the ring of scalars. So when I do the trace, it's just 2 times it. So the 2's cancel. Okay, so that proves the trace part, and then the determinant part follows from this and the fact that it satisfies that polynomial. Okay. And so, of course, it's very important when I wrote those original equations. So, mark, when I write like the determinant of F, so I had written in the statement of the proposition, determinant F equals P. It's very important here that you're taking the determinant in the sense of, an endomorphism of the T module. It's not true if you think of this as a bigger dimensional QL matrix and take its determinant. Okay, are there any questions about this? All right. So now I want to use this to study what people call Shimura's construction. It's a way to take a modular form and associate an abelian variety or an Galois representation. Yeah. Wait, so how are you getting determinant P? What did you say? Yes. Yeah, that's right. I mean, I think that's basically what I did, though. I mean, you need to know that they're dual operators like TP linearly. That's. I mean, well, Eichler Shimura is telling you that it satisfies the quadratic equation with TP as the coefficient. So if you want the trace to be TP, you need Eichler Shimura. Yeah, so maybe the determinant part's easier. But yeah. Okay, so we're now going to fix a prime number n, and we're going to let f be a weight 2 class form for gamma 0 n, normalized eigenform. Okay, so I'm going to let alpha be the homomorphism from the Hecke algebra to C. It gives the eigenvalues of f. So this is defined by Tp acting on f is equal to alpha of Tp f. And it's also the case that alpha of Tp is equal to AP of f, since f is normalized. All right, I'm going to let K be the image of T tensored up with Q. So this is a number field. I'm going to let O just be the image of T, which is some order in K. And I'm going to let this math frac A guy be the kernel of alpha, which is an ideal in the Hecke algebra. Okay, and now the important definition. I'm going to define AF to be the quotient of J0n by this ideal A. So here by A times J0n, I mean the sum over all T in the ideal A of Tj0n. So each one of these Tj0n is an abelian subvariety of J0n, and then I'm summing them all up. Okay, so this construction really is only going to depend on this ideal A. It's not really sensitive to F. I mean, giving F is really like picking the complex embedding of K, and that's not actually going to be needed. And also the assumption that n is prime here is not needed. You can do it with composite n, but then you have to worry about new form, old form stuff. I just wanted to avoid that. All right, so the first thing I want to say is what the dimension of this AF is. So the tangent space of J0n, so this is the Jacobian of x0n, so it's the space of one forms on x0n. And this is equal to, at least over the complex numbers, this is equal to the space of cusp forms. And so this, we proved, was a free module over the Hecke algebra over TC of rank 1. And so by the same sort of reasoning that we've done before, this thing, so if I mean this over Q, it's going to be a free rank 1 module over the rational Hecke algebra. So if I look at the tangent space at the identity of this AF, well, this is the tangent space of J0n mod A tangent space of J0n. And so this is going to be a free, well, it's going to be a one-dimensional K vector space. Right, I mean, each one of these guys is a free rank 1 module, so the quotient as a T module just looks like T mod A, which is O. well, tensored up with Q, which is K. Okay, so that says that the tangent space is a one-dimensional K vector space, so that tells us the dimension. So the dimension of this AF is the degree of K over Q. Yeah, T0n is a free TQ module of rank 1. Well, I mean, just think of it as like, here's a free module of rank 1. This is the same thing, so I'm just doing this free rank 1 thing mod A. So I mean, as a T module, that just looks like T mod A. And if I've tensored with Q, then T mod A is K. Okay? Yeah, I mean, I think if you just think about how that works, it works out. I mean, I think that's clear over C at least, and then that reasoning just holds in general. Yeah, but I mean, you want to say that like if you take 2 abelian subvarieties and sum them, then the tangent space is at the origin sum and that sort of thing. Works out. Okay, good. So we know the dimension of this thing. And so as a corollary, I guess I should just point out, this is kind of an important special case. This guy is an elliptic curve if and only if K is Q. It's the same thing as saying that the Fourier coefficients of F are rational. Right in the famous conjecture about all elliptic curves over Q being modular is saying that they all come from this construction. But that's a different story that we're not going into. Okay, another simple result. AF has good reduction away from N. Okay, can someone tell me why that's true? Yes. Yeah, right. So let me say why that works, because that's a good application of the criterion. So first of all, first J0n has good reduction away from N. Because it's the Jacobian of a curve that's smooth over Z join 1 over N. And so now we just use this lemma, which is what Ari was saying, is that if B is say B is an abelian variety over a DVR with good reduction, and say that A is a subquotient of B, then A also has good reduction. And the proof is to just use the Narrow-Nagshoff-Ravitch criterion. So pick a prime L, pick an invertible prime L, then B has good reduction, implies by the Narrow-Nagshoff-Ravitch criterion, or actually this is the easy direction of it, that the L-adic Tate module of B is an unramified Gauss representation. right? And saying that the representation is unramified means that the inertia subgroup acts trivially. And that obviously goes through to any subquotient. So that implies that TL of A is unramified. And then by the harder direction of Naranov-Shafarevich, that implies that A has good reduction. Okay, so if you start with something with good reduction and do kind of any linear operations to it, you're not going to pick up bad reduction. And so that's what we're doing here. We're starting with J0n that has good reduction, and we're kind of building some quotient of it, so it's going to keep good reduction. Are there any questions so far? All right, so this O that I defined, which was T mod A, acts on the AF, right? I mean, T acts on AF and A is acting trivially, so O acts on it. And so that implies that the L-adic gate module of AF we can think of as a K tensor QL module. And in fact, we know that it's free of rank 2. So now suppose that we have a prime different from L or N. So this L-adic Tate module is a representation of the absolute Galois group. And since we have good reduction away from N, we know that it's unramified at P, away from Ln. We want to know what Frobenius at P, how it acts on this. And the statement is that its trace, so Fp is the Frobenius at P. Let me just call this VL. The trace is equal to AP, and the determinant is equal to P. And we've basically already proved this. This is something that you just check mod P, right? We're just talking about the Frobenius at P. So you can check this by going mod P, and then it just follows from the previous statement that I made about how it worked with the full Hecke algebra. So we had previously shown that the trace of Frobenius on VL of J0n is TP. And the point is that we have this surjection from J0n to AF, just by definition. And that's compatible with the actions of F and T. So the trace of Frobenius down here is just going to be, sort of TP again, which is equal to AP, since we've killed A. That's all that's going on. Okay, any questions about that? Yeah. No, I don't think so. No, but you should keep in mind that, for these kinds of things that we're doing when we're working rationally, the Hecke algebra then just decomposes the product of fields. So this VL is just gotten by applying some idempotent. So everything's like a summand. So everything works as nicely as you'd want. Yeah, okay. No, I think it's not true though that it's always maximum. All right, so now we can prove the existence of Galois representations associated to modular forms, which is an important thing. So we have to choose an embedding of the coefficient field into QL. I'm just going to use QL bar. So then here's the statement. there exists a unique, up to isomorphism, semi-simple representation rho from the absolute Galois group of Q to GL2 QL bar such that, so three things. First of all, rho is unramified away from N and L. Two, this is the really important one, the trace of Frobenius at P in this representation rho is AP. AP of F, I mean. And third is that the determinant is cyclotomic. All right. So the idea is just to take a piece of the tape module of this AF. So, I mean, if K were the rational numbers, then just the tape module of AF would already do the trick. But if K is bigger and it has some splitting, then we have to take a piece. That's basically all. So let me call this I. So the choice of I determines an idempotent of K tensor QL. Say P. Right, when I take this number field and look at it over QL, it's going to split into a bunch of places corresponding to the primes over L. So here I'm just picking out one of those places. And so we already know that if I look at the rational tape module of AF, that it satisfies these conditions. Well, maybe ignore three. The determinant of FP is P on it. Regarding it as a module over this ring. And so I can just take the sum end corresponding to E, and those equations will still hold. So we can take rho to be, well, I want it to be semi-simple, and we don't know anything about that yet. So let's say, take it to be the semi-simplification of E applied to VL of AF. So we know that rho is unramified away from N and L. Right, because we know that for the full VL. We know that the trace of Frobenius is AP. And we know that the determinant of Frobenius is P. This is for all P away from NL. Okay, and then that implies that the determinant is cyclotomic. So in chi L of FP is equal to P. So these two characters agree at all Frobenius except for N and L, so they must agree. So this implies the determinant is cyclotomic. Okay, so that proves the existence part. The uniqueness part is easy. So say that we had a second representation. So then the point is just that the trace of rho of Frobenius is equal to AP, and that's the trace of rho prime. That's just what condition 2 says. So all these Frobenius except for N and L have the same trace. And so the Chebotarev theorem says that these Frobenius are dense in the Galois group. So this implies by Chebotarev the trace of rho of G is equal to the trace of rho prime of G for all G in the Galois group. So rho and rho prime are semi-simple representations with the same character. And that implies that they're equivalent. Okay, any questions? Yeah. I said it goes to GL2 QL bar. Right, the point was that this guy here, this VL of AF, was two-dimensional over this. It was a free rank 2 module over this. I mean, the whole point is that the original VL of J0n was free of rank 2 over T. And then we basically just hit it with 2 idempotents. We first went down to this AF thing, and then we went a little further. And so it's still going to be free of rank 2 over that piece of the ring. Well, that'll give you, I mean, so there's this choice of embedding, right? And as you vary the embedding, you're going to like kind of apply Galois things to the coefficients of the representation. Okay, so we said that there's this unique isomorphism representation row satisfying these conditions. I mean, semi-simple. And the reason that we have to include semi-simple in there is because we were only giving conditions on the trace and determinant of elements, and that only detects it up to semi-simplicity. So those kind of conditions can, I mean, only ever tell you about the representation up to semi-simplification. In fact, it's true for the representations that we're getting here that they're irreducible. But I'm not going to prove that now. So actually, if you went to Stefan Petrikas's GLNT seminar, he sketched a proof of the irreducibility. So I guess I should emphasize that this is a very important thing. We went from a modular form to a Galois representation. That's a generalization of what goes on in class field theory, going from like a Hecke character to a character of the Galois group. It's kind of the first step into non-abelian class field theory in the Langlands program. This is a very big deal. Okay, so I want to do one more thing today, just as an application of this. That's to go back to, remember we proved this multiplicity 1 theorem, I think last time. So we can use this to give the proof of the strong version of that theorem. So strong multiplicity 1. Okay, so the statement, suppose that, well, again, n is going to be prime, but that's unnecessary. We have 2 normalized forms, not necessarily eigenforms, just have A1 equals to 1. And suppose we have some set S, density 1 set of primes. And suppose that for all the primes in S, F and G are eigenvectors of TP and have the same eigenvalue. The conclusion then is that F equals G. So what we proved last time was that if F and G were eigenvectors of all the TP, except for P equals n, where we don't have a TP, with the same eigenvalues, then they're equal. So here it's a much weaker hypothesis. Okay, and so the idea is to just use the Gao representations in Chebytarov and transfer that back. So here's how it goes. So let alpha be the function giving the eigenvalues. So TPF is alpha of PF for P and S. That's what I mean. And define V to be the space of cusp forms that transform in this way. So that's some subspace of S2n. And we're trying to show that it's one-dimensional. All right, so since that Heck algebra is commutative, and S2n has a basis consisting of normalized eigenforms, the same is going to be true of V. Normalized eigenforms for the full T. And so in fact, it's enough to show if I have two guys in here, which are normalized eigenforms, with the full T, then they're equal. Right, because that will show that my basis consists of one element. All right, so let K be the subfield of C generated by the coefficients of the H's. And choose an embedding of this into Q of R. So given that choice, we get Gao representations, rho and rho prime. Associated to H and H prime. And so these have the property that rho of Frobenius is AP of F, AP of H, and rho prime of FP, or sorry, the trace of these guys is AP of H prime. And this is for all P not dividing NF. And so this means that the trace of rho of Fp is equal to AP of H. And if P is in S, this is equal to AP of H prime by assumption. So this holds for all P in S by assumption. And so again, by Chebytarov, these Frobenius are dense in the Galois group. And so that implies that these traces are equal everywhere. And so now if we have any prime, so if P is any prime not dividing NL, then AP of H is the trace of rho on FP. And now we use that this is equal to the trace of rho prime on FP. Right, the point here is that we're approximating this FP by Frobenius that live in S. But here we've forgotten L, but we're free to choose L to be whatever we want. So if we use two L's, we get that AP of H is equal to AP of H prime for all P that are not equal to N. And by the weaker version of multiplicity 1 that we proved before, that says that H equals H prime. You have a question? Okay, any questions? Okay, well that's all for today. So next time, yeah, I know it's early again. So next time we're going to start on this criterion, theorem A from the first lecture, which gives a kind of abstract criterion for elliptic curves over Q not to have n torsion for n some fixed prime. Okay.